Harmonic Gestalt, sound from structure, a holistic invariant representation of spatial structure through sound as a model of perception. Part 1. The Paradox of Visual Experience. The phenomenon of vision is a truly remarkable phenomenon. We simply open our eyes, and there's the world in full 3D and color. And if we look around in different directions, we see the world in different directions. The world appears where we point our eyes. The visual world appears as a surrounding spatial structure, complete with an image of ourselves viewing it. When we have visual distortions or hallucinations, they don't appear in our head where the distortion occurs, but out in the world among the objects of perception. When we see a bright light or a camera flash, it burns an image on our retina that follows us wherever we direct our gaze. And when we close our eyes, everything disappears except the afterimage. But it appears out in the world in front of us instead of inside our eyeball, where we know the afterimage to actually exist. If the bright light was in the form of an erect arrow, then the afterimage is also an erect arrow, even though the corresponding image on our retina is known to be inverted. How does the retinal afterimage get uninverted again? These aspects of experience are deeply paradoxical. Why is the world not inverted like the retinal image? How does the retinal afterimage turn right side up? These are old questions that used to be the subject of deep inquiry, but nowadays they're generally glossed over as a pseudo-problem. But this is by no means a pseudo-problem. This is significant because it determines what the visual system actually does. Is vision a passive, receptive process detecting information from the world? Or is vision an active, projective process constructing a perceptual world? Part 2. Amodal perception and perceptual reification. Albert Bichot coined the term amodal perception to describe the perception of the whole of a physical structure when only parts of it are directly visible. For example, this red pencil here is perceived to be a continuous object through the occlusion provided by the green pencil. It's a kind of perceptual completion or cognitive filling in of the missing information in the sensory data. So there are two aspects to visual perception. There's the direct experience of colors seen on colored surfaces that are exposed to direct view. But there's also an invisible structural framework on which those colored surfaces are perceived to exist. So the modal aspect of experience is the direct sensory experience, whereas amodal perception is the invisible framework on which the modal surfaces appear. The amodal percept is easily confused with the real world itself, except that it is not always real. It is indeed a construct of our mind. Amodal perception is every bit as essential an aspect of visual function as is sensory experience. For example, the information content of the experience of a tomato held before your face is of a round colored surface exposed to your view, but that is not your complete percept. We perceive the tomato as a whole object, as if we could see invisibly into its internal structure. If we have any experience with tomatoes, we can even imagine the arrangement of seeds and fleshy tissues in the tomato, even as we view its front face. So depicted from the side, if this is our viewpoint, the side of the tomato exposed to view appears as a modal surface percept, but the rest of the tomato appears as an invisible amodal volume percept. We see the volume in the tomato. It's kind of like a combined experience of both the modal surface and the amodal experience. Amodal perception is the first stage of cognitive processing, and it is a volumetric image. Vision is a constructive or generative function, as demonstrated here with the Canizza triangle, whereas an illusory triangle is perceived to occlude three dark circles, complete with a percept of the illusory contour with an actual brightness difference across the illusory edge. So the experience contains more explicit spatial information than the sensory stimulus on which it is based. This is an example of the perceptual principle of reification. In fact, the Canizza figure is really a three-dimensional percept composed of modal and amodal components. The modal components are the dark circles with their cutouts. The amodal component is the boundary of the invisible circles that are occluded by the foreground triangle. In actual fact, they are perceived to be behind the triangle as complete circles. We see also the difference between this modal percept of a box on which every point on every visible surface appears at a certain location in depth, whereas in this amodal wireframe picture, we see empty space. We see also a difference. This is a visual illusion with a modal component introduced by these V features. If you remove the V features, you still see the triangular configuration. You can still draw in the triangle that you perceive amodally, but you don't see the modal color along the illusory contour. Even more impressive examples of spatial reification can be seen in Prägnanz's volumetric worm, which appears as a spiral black worm wrapped around a white cylinder. Here also a similar example, Prägnanz's sea monster, in which these three objects are seen as a continuous single snake that emerges from the water surface at a particular angle indicated by the ellipses of where it intersects the surface. So perceptual reification is an extraordinary visual function. How the visual system performs spatial reification remains a deep, dark mystery. But that it does so is an observational fact. The primary function of the visual system is the generation of a volumetric, three-dimensional, real-time, moving colored image of the world in experience based on information from sensory input. Part 3. The ontology of visual experience. All this raises the question, where is the picture in our experience that appears when we open our eyes? Is it out in the world before us, or is it somehow inside our head? This is an ancient debate that goes back to whether perception is direct or indirect. Direct perception, or naive realism, is our natural, intuitive understanding of vision that we see the world around us as the world itself. Indirect perception, or representationalism, suggests that the world we see around us is a perceptual replica of that world in an internal representation. This is a profound philosophical dichotomy, and it's central to the understanding of the principles of vision. And this issue, incredibly, remains unresolved to this day. I propose that this is the single greatest obstacle to further advance in understanding of the essential principles of vision. So, according to direct perception, or naive realism, the world we see around us is the world itself. The problem with this view is the causal chain of vision. Light from the world enters our eye, where it is transduced to an electrochemical signal, which is then sent from the eye to the brain, where it stimulates a pattern of electrical activity, which has the consequence of us experiencing the visual scene. So the appearance of the conscious colored percept is causally dependent on the presence of this pattern of activation and not in direct contact with the activation that causes it. The problem is that the vivid spatial structure that we see in experience appears at both ends of the causal chain, both as the source and as the final result of visual processing. Direct perception fails catastrophically in the case of dreams and visual hallucinations where there is no objectively real object as the object of perception. It also fails catastrophically in the face of visual illusion, where illusory objects are perceived where there is none in the stimulus. Indirect perception, or representationalism, suggests that everything that you perceive around you is an image in your brain. The problem with this scheme is that it suggests that everything around you is inside your head, an idea that is so preposterous that many consider it not even a serious alternative in contention. People have come up with all kinds of alternative schemes to try to get around this issue. For example, some people believe in projection theory, that experience is a spatial structure produced by the brain, but is projected out of the brain again to appear superimposed on the world. The problem with this theory is that nothing has been detected projecting outward from the brain. Max Wellmans, the modern proponent of this projection theory, insists that nothing physical is projected, it is just experience that is projected. Well, the first problem with this is it's an unfalsifiable hypothesis because its prediction that nothing will be detected coming out of the brain is identical to the null prediction that nothing is actually projected from the brain. Furthermore, this projection theory diverts the most interesting part of the problem of vision to outside the world of observable science. Then there is the philosophy of eliminative materialism, championed by Daniel Dennett, that consciousness does not exist as we experience it to be, but rather that consciousness is an illusion, that when we think we are seeing a three-dimensional colored spatial world, what is actually happening in our brain is just a mass of electrical activity which corresponds to our experience without the necessity for any kind of actual pictures in our brain. Whether the image of experience is an explicit spatial structure in your brain, or whether that image is projected out of your brain into the world, or whether you can have a spatial experience in the absence of an explicit neural representation in the brain, in any case, whatever the ontology of the image of experience, that image is the essential product or output of the visual system without which vision would be useless. The image that is my experience has an objective reality as an object in my experience. That object is an essential component of my visual function. The image of our experience is therefore a valid subject of scientific scrutiny. Indeed, no model of vision can be complete without this essential component. Part 4. Perceptual modeling. The reality of the visual percept motivates a perceptual modeling approach in which we describe vision as an input-output function beginning with a two-dimensional visual stimulus and ending with a three-dimensional perceptual object. For example, this figure here stimulates a three-dimensional percept of a box in a corner, so the perceptual transformation is the transformation from this two-dimensional stimulus into this vivid three-dimensional percept. In the case of Peter Tsay's volumetric worm, the perceptual transformation of this two-dimensional stimulus is this three-dimensional object. Now we see a regular spiral cylinder with hemispherical end caps wrapped around a white cylinder, complete with amodal completion behind the occluding cylinder. There's obviously some kind of simplicity metric in effect here, where this is judged as the simplest interpretation of that particular stimulus. And the simplicity metric appears to be based on symmetry, the circular symmetry of the cylindrical cross-section, the spiral symmetry of the central axis, and the circular symmetry of the occluding white column. This is the Gestalt principle of Prägnanz. The simplest interpretation is the one that the visual system seems to prefer. But that symmetry must be detected in full 3 dimensions because there is no symmetry in the two-dimensional projection. Likewise with Peter Zay's sea monster, the perceptual transformation goes from this to this, complete with a percept of the amodal completion of the serpent under the milky surface of the water. Again, there appears to be a simplicity metric in effect here, but the symmetry must be detected in full 3 dimensions because there is no symmetry in the 2-dimensional projection. This leads to somewhat of a chicken and egg problem because the perceptual image must be reified before you can even detect its symmetry, but the symmetry is required in order to reify the perceptual image. This is indeed a manifestation of the inverse optics problem. All of these quadrilaterals project to the same retinal image because the optical projection of the eye collapses them all of these 3-dimensional shapes into a 2-dimensional projection in the normal optical projection. The idea of the inverse optics problem is to attempt to invert the projection, and from this one rectangle, we'd like to reconstruct all of the possible rectangles that could possibly have projected to it. Now, this is a mathematically under-constrained problem because there are an infinite range of quadrilaterals that all match to this surface. So this is practically impossible to compute using normal sequential algorithms. How on earth does the visual system resolve the inverse optics problem? Part 5, Gestalt theory. Gestalt theory is a holistic field-like principle of computation that defies explanation in conventional computational terms. The principles of emergence, reification, multistability, and invariance are prominent aspects of visual function. Emergence is seen here in this dog picture, known well in vision circles as a picture of a Dalmatian dog under the shade of overhanging trees with its tail up in the air here somewhere. You can see that this picture emerges spontaneously from the coincidental alignment of innumerable local edges that suggest 3-dimensional surfaces. You can actually see the surface of the dog's back by an emergent principle. Reification we have already seen in the case of these visual illusions. Multistability, there are percepts that can pop back and forth between 2 alternative interpretations, suggesting that the perceptual system is itself multistable. And invariance is the ability to recognize shapes invariant to factors such as their rotation, their translation, and their scaling by perspective. These shapes in A here are easily distinguished from these shapes in B, even though they're composed of the same elemental components, and they are still recognized through various different distortions, including perspective distortions and morphological transformations, and even despite expressing the shapes in different perceptual primitives. Wolfgang Köhler, in his book on Die physische Gestalten, describes systems that exhibit Gestalt emergence, showing that there's no magic in emergence. There are certain kinds of systems that have emergence. For example, water seeking its own level. How does the water know exactly what level to appear in each tube? Well, it's a matter of every particle of water pushing on every other particle all at the same time, and they're all moving at the same time until they reach an equilibrium. Emergence is also seen in the distribution of electric charge on a conductor, where the charge distributes itself more densely at high curvature points and less densely at low curvature points, and it instantly re-equilibrates whenever additional charges are added. The soap bubble is also used as an example of Gestalt emergence, where the spherical shape of the soap bubble is not defined in any mathematical formula or template, but rather it emerges by the simultaneous parallel action of every part of the surface pulling on every other part simultaneously. And emergence is seen in the phenomena of waves and resonance. Indeed, I propose that harmonic resonance is the ultimate Gestalt phenomenon, exhibiting as it does all of the Gestalt properties of emergence, reification, multistability, and invariance. Now, a word about paradigms of computation. We're all familiar with the analog paradigm, where you have analog electronics working on analog signals, and digital, as in modern computers, where we have digital components connected, processing digital square wave type signals. Both of these paradigms exhibit discrete computational elements connected by discrete wires in a circuit network. I'd like to introduce a different paradigm of computation, the spatial computational paradigm, which involves spatial computation across a spatial medium. For example, the game of life is a spatial computational algorithm. The algorithm depends on the spatial arrangement of the pixels, and the interactions between the pixels are spatial interactions. This is, of course, a digital form of a spatial computation. Here's an analog principle of computation in the Grassfire algorithm. This is an algorithm used in image processing to compute the medial axis skeletons of various geometrical shapes. So for instance, for this rectangle, we ignite a grassfire, metaphorically, around the perimeter of the field, and then we track the flame fronts as they advance in towards the center of the figure. At points where two flame fronts meet, or along the center where opposite flame fronts meet, you mark the central axis skeleton. So this is, again, a spatial computation across a spatial medium. Again, it can be computed in digital, on a digital computer, but the algorithm must perform as if it was performing on a spatial field. The most impressive spatial computation is seen in the optical Fourier transform that is performed by a simple lens. And if you take an input image like a photographic slide, in this case of a sinusoidal grating, and you place it at one focal length of the lens, and over on the other focal length you place a frosted glass screen, and if you illuminated the input image with coherent light, like a collimated laser beam, then this lens performs a Fourier transform on this image. And it's all done by analog computation, waves passing through the lens and intersecting and overlapping. And remarkably, this mechanism also does the inverse Fourier transform. The glowing of these three spots is inverse transformed into a sinusoidal grating again. And ripples on a pond can be seen as an analog computational mechanism. It may not actually represent anything beyond itself, just the waves, but ripple tanks are often used to demonstrate optical phenomena, and therefore the ripples on a pond are a spatial computational medium that follows certain spatial laws. And perhaps the most impressive example is the principle of phase conjugation, where laser beams crossing in space create interference patterns. Now, if these two laser beams cross in space, this is the kind of interference pattern that they create that lines up with the angular bisector, the angle between the two beams. Now, if this intersection takes place within the solid volume of a transparent nonlinear optical material, and just about any glass goes nonlinear if the amplitude gets high enough, then this pattern of diffraction actually warps the glass in the same pattern as the diffraction. And this means that when other beams are sent in here, for example, this is the same situation we have over here. We have beam 1 coming in from here, beam 2 coming in from here, and now we get a probe beam, and it can come in from any direction you like, but if it comes in and it hits that zone of intersection, it reflects and refracts off the interference pattern and makes a reflected signal beam coming out this side. A wave vector diagram can predict how these things go, starting from the origin. The beam 1 makes a wave vector k1, and then beam 2 makes the wave vector k2. So this point in the diagram is the position of k1 plus k2. Now you send in the probe beam coming in from here, that's k3, and the wave vector diagram will be closed by k4 that goes from the last point to back to the origin again. It always has to go back to the origin, and this completion of the circle into the origin is what produces the reification in phase conjugation. So in order to produce a phase conjugate mirror, all you have to do is take the probe beams, beam 1 and beam 2, and point them at each other, anti-parallel to each other, and they will create a standing wave inside this area of inside this tube. And now the probe beam comes in over here from whatever angle it chooses to come in from. And from the wave vector diagram, the K1 and K2 cancel each other out. So when K3 comes in, it must create a K4 to close the wave vector diagram, and K4 is the phase conjugate beam. It's the time reversed beam that turns the incoming beam 3 into a standing wave as it mixes with the outgoing wave B4. So how does this work? In a regular mirror, an incident ray is reflected off the surface and comes back out the same way that it came in. In a phase conjugate mirror, similar behavior is observed, that it reflects off the volume of interference patterns inside here and goes back out the way it came. Now, when the light comes in at an angle, where the angle of incidence equals the angle of reflection, the phase conjugate mirror does something different. It goes reflected back out again, reversing the incoming ray. And this has some rather interesting properties. For example, if you have a coherent beam of light or some kind of image, and you send it through a distorting glass, wavy kind of bathroom glass, then it distorts the image. And when you reflect the reflection of the image, it will go back through the distorter on a second pass and get even more distorted. In a phase conjugate mirror, something very strange happens, that the distorting glass does indeed distort the incoming beam, but then the reflection traces back the distorted beams right through the distorting glass and undistorts them again. This can be done with amplification. This is a remarkable wave-like computation which has direct significance for the brain. Part 6, Properties of Harmonic Resonance. Harmonic resonance, even in its simplest forms, exhibits some curious properties as a spatial computational system. Consider a simple resonant tube like a flute. When you blow a note in a flute, a pattern of standing waves emerges in the body of the flute at the same time as a sonorous tone, a harmonic tone, emerges. Here are the first through fifth harmonic shown here on a vibrating guitar string, but this could also be considered an amplitude function on the air pressure in the flute, which oscillates mostly in the middle for the first harmonic, and the second harmonic that has a high pressure, low pressure, alternating with low pressure, high pressure, third harmonic, high, low, high, alternating with low, high, low, and so on through the fourth and the fifth harmonics. The first harmonic is the dominant one. It's the one you principally hear. The higher harmonics are just ringing on that fundamental. So what this mechanism does is it automatically reifies every periodic subdivision of the tube simultaneously and in parallel. This is a truly magical process, the only physical system that defies entropy and creates order out of chaos. Now, the harmonics in a tube can be modulated or filtered by opening a hole like the holes in a flute. And what this does is it automatically damps any of the waves that have a high amplitude vibration right at the location of the hole. So if we look over here, the yellow here is the first harmonic, then the red is the third harmonic, and the pink is the sixth harmonic. And when you open a hole right here, all those harmonics are damped because the hole kind of short circuits the air pressure here and allows contact with the outside air. So this leaves, in this case, only the second harmonic in blue and the fourth harmonic in purple and the sixth harmonic. These are indeed the even harmonics. The damping creates a mirror symmetry out of the patterns in the tube. Now, if you open a second hole, say a 1/4 distance along the flute, then this will damp selectively those oscillations that have a high amplitude right here, in this case the second and the sixth harmonic, which leaves only the fourth harmonic left that is consistent with this input. Now, curiously, when you damp this quarter length of the tube, there's also a virtual damping that appears over here because it's the fourth harmonic. So any energy over here leaks out through the hole at the quarter distance. Here are some Chladni figures produced by bowing a steel plate with a violin blow while damping the plate with a touch of the finger. The patterns of standing waves are revealed by a sprinkling of salt or sand that settles along the nodes where vibrational pattern is minimal. Here's the Harvard Natural Science lecture demonstrations for Chladni plates, starring Daniel. Notice how he touches a plate to create a node. Here he's putting 2 points right next to each other. That creates a very high frequency harsh sound. The patterns on a square plate are constrained by the square shape of the plate. Where he bows it, it tends to form an antinode with periodic nodes in between where the salt or the sand collects. See how the touch of his thumb induces a node to form here. The damping touches with your finger are like the input to this system, and the harmonic resonance responds to the input. Here's Mary Waller from 1961. She developed a different way of making the plates resonate. She uses a piece of dry ice held in a pair of tweezers and presses it against the steel plate. Here is a plot of the many different patterns from Mary Waller's book that she managed to elicit from a square steel plate. The patterns on the upper left are lower frequency patterns, lower energy, and going down towards the lower right, they get higher and higher energy, and these are harsh screeching sounds. Now, if you damp the plate, now this is just one plate, I was showing the many patterns on the plate, but if you take that one plate and you damp it at the upper left corner, you kill off all the patterns that are not that do not have a node in that upper left corner. So that leaves only the patterns shown here outlined in yellow that do have a node on the upper right. So by damping at this point, you selectively mute all of the patterns that are inconsistent with this input. If you touch the top center, again, this is the same plate, then you highlight all of the nodes all of the patterns that have a node at the top center. And if you touch both at the same time, you get selectively only those patterns that are consistent with both the damping on the upper left and on the lower right. This is an extraordinary system of pattern primitives based on symmetry, arranged in a hierarchical order based on Prägnanz. It does not just find the simplest pattern, it finds all of the patterns that are consistent with the given input. And it reifies all of them simultaneously and in parallel unless excluded by further inputs. The competition between alternative interpretations occurs by constructive and destructive interference between the competing reified standing waves. Part 7. What can you do with resonance? In order to demonstrate some of the extraordinary properties of simple harmonic resonance, let's take a look at Paul Falstad's most excellent math and physics applets on oscillations and waves. We're going to focus on the box modes applet. This represents resonance in a cubical box. We're going to rotate it a little bit so you can see it in 3 dimensions. And this is the first harmonic oscillation in X, represented here by this square 100. And what we see here is an oscillation across time of air pressure, and in the case of acoustical system, where, say, green is overpressure and red is under pressure, and you see that the overpressure hops back and forth from one side to the other. It is a cyclic representation of what is actually a static pattern. Here's the second harmonic in X, and you see this goes green, green to red, green, red. And here's the third harmonic, and you can see you get higher and higher harmonics all in the X dimension, and likewise you could do the same. Here's the first harmonic in Y, the second harmonic, and so forth. There are 4 kinds of information that are encoded in the standing wave. First of all, there is the raw oscillation, the alternating pattern of air pressure. But if we ignore the phase and just observe the magnitude, we can see the magnitude value is another set of patterns. Or we can ignore the magnitude and just look at the polarity of the wave, and now we have a crisper, more geometrical kind of representation of shape. And finally, there's the nodes of the oscillation, the planes in this case, where there is no oscillation because it's between the positive and negative modes. This, I think, is the most promising aspect of harmonic resonance as a representation of geometrical structure. To give an intuitive understanding for the kind of mechanism required here, imagine a 3-dimensional cubical box, kind of like a speaker cabinet, with 3 speakers mounted in XYZ, but they're mounted on the outside pointing into the box, so they'll trap the standing waves inside the box. If you attach these 3 speakers to 3 signal generators, then they would be able to set up the standing mode vibration of the patterns that you see in Falstad's simulation. Or perhaps a better model is a harmonic keyboard, like an organ keyboard, where these represent the actual harmonics. They are a musical scale, and when you press these, it's equivalent to the box modes applet. Okay, back to the box modes applet. Here we have the first harmonic in X, the second harmonic in X, the third harmonic in X, and so forth likewise in Y. Now you can also turn these harmonics on at the same time. For instance, first harmonic in X and the first harmonic in Y. What this does is a voxel for voxel summing of the values of the X pattern and the Y pattern. Now the X is positive on top. Well, let's stop the oscillation so we can pick an exact phase. So here's X and here is Y. So X is positive to the left and Y is positive on top. If you turn them both on at the same time, then it's positive in the top left. So if this pattern is called X, this is the first harmonic in X, and this pattern is called Y, first harmonic in Y, then X plus Y is this pattern over here, and X times Y is this pattern here. And notice that there are two polarity reversals, and here they are two polarity reversals, and a minus times a minus makes a plus. That's why the bottom corner here is positive. So here's the full repertoire of patterns in X, Y, and Z. Well, not shown in Z, but actually there's a third dimension Z back there. So this is all the patterns that you can make. These are actually all the static patterns that you can make. Now, the different harmonic modes operate at different frequencies. The first harmonic oscillates at half the frequency of the second harmonic, and likewise with the third harmonic. Now, if you turn them on individually, they define static patterns. And actually, this interface even tells you can turn them on in combination between X and Y, and maybe even Z, because those three are all at the same frequency as indicated by the highlight. If, on the other hand, we mix a first harmonic with a second harmonic, that now defines a temporal pattern, and it's a cyclic temporal pattern, and it is expressed in the exact same way as the static patterns. Now, what happens if we turn on a whole array of these patterns? Look at this. This looks like a positive plane in a negative field, and the more higher harmonics I turn on, the higher the resolution of it is. Now, this is an extraordinary dynamic pattern. I'll call this a windshield wiper, left and right. And of course, you can do the same thing in Y. Now, if we turn on the harmonics in X and at the same time the harmonics in Y, then what we'll get is a sum of the two patterns in X and Y. This software can only do so many higher harmonics, but you can see what it's trying to do here. We've got the original windshield wiper going left and right vertically. Maybe we'll speed it up a little bit. And now we got also the horizontal plane moving up, down, vertically. We could add the Z dimension as well by turning on a bunch of these. But alternatively, instead of summing the patterns, how about we'll try the product of these patterns. And if we add the higher harmonics, what is that pattern that's emerging now? It is a pattern in X and Y, and it starts as a plane in a diagonal, then it opens up into an open-ended box, and then it closes to a plane on the other diagonal. Again, another extraordinary three-dimensional dynamic feature representing a very specific kind of motion. Now, you can generalize this concept into three dimensions. Instead of a diagonal in X and Y, we'll do diagonal in X, Y, and Z by clicking 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, 4, 5, 5, 5, 6, 6, 6, and 7, 7, 7. What the heck is this pattern? Let's try cycling it. What we have here is two tetrahedrons, or one tetrahedron that turns inside out and morphs into another tetrahedron. And the one tetrahedron is defined on the primary axes, X, Y, and Z, whereas the other tetrahedron is defined on the other axes, X, Y, Y, Z, and ZX. This is a three-dimensional generalization of the same concept as that open-ended box, opening and closing again, but adding the Z dimension. Now, we've tried the patterns with these regular series of harmonics 1, 2, 3, 4, 5, and 6 in X, and we get the windshield wiper going left and right. If we shut off all of the all of the odd harmonics, we get a different pattern. Now it is like two hands clapping. Two positive planes that meet in the middle, reflect off each other, and go back to the outside. How does that compare to the even harmonics? Well, we'll shut off the odd harmonics and turn on the even harmonics, and now what do we get? It also is two hands clapping, but this time it's a plus hand and a minus hand, and the plus hand makes it all the way across to the other side before reflecting back and clapping with the other hand. So this is another primitive that's related by the second harmonic. Okay, let's look at the spatial generalization of concepts. This here, the second harmonic in X is a spatial concept. We will consider it a static pattern for now, and it alternates between plus, and minus, plus, minus. So we can consider this the sandwich concept, one phase in the middle, the opposite on the outsides. We can also find the corresponding phase over here in the y dimension. It's a y sandwich. Now, what is the generalization between an x sandwich and a y sandwich? Well, it becomes this guy here. It's a negative cylinder inside of a positive surround, but it's a pattern in x and y, not in z. And if we add the z component, then what we get is a three-dimensional sandwich, or a sphere surrounded by non-sphere. Okay, let's take a look at another dynamic spatial concept. We'll turn on the first harmonic in X and the second harmonic in Y. Now this creates this dynamic pattern. It's a pattern defined in X and Y. We'll slow it down here, and you see that what it is, it's a sandwich, and then the plus goes off to the right, and then it penetrates the minus and goes off to the left. So if you observe this pattern, you could call this dynamic pattern penetration in X and Y. Now, if we want to generalize this concept, we can add a z dimension to the pattern, and now it becomes a cylinder puncturing a slab and then reversing and puncturing the slab again. Another three-dimensional spatial concept. Now, there's one more dimension of control, and that is by controlling the phase. If we stop this oscillation of the first harmonic in X, and we zoom in really close to this little square, if we click on the square and drag to the right, it will change the phase of the fixed wave like a radio tuning dial. So the little blue line over here, think of it as a radio tuning dial. You have to move your mouse way the hell out here in order to change it, and take a look at what it does. At zero phase, it's whatever it was, in this case, minus plus or red-green. As we advance in phase, it's as if you're going forward in time in the cycle, and there it comes up with the reverse phase. And if you continue, it will reverse again. Now, isn't that curious? We can see the significance of this. Let's return that phase to 0. If we turn on X and Y coordinates and we continue the cycle, if I advance the phase of x relative to that of y, it begins a clockwise rotation. If we advance the phase of x even further, the clockwise rotation reaches a maximum and then slows back down again. The maximum rotation rate, there it is now, it's static at half phase. I'll go back a little. The maximum rotation rate is achieved at counterphase, 90 degrees advance. And then it tapers back off again, and now it's just straight 180 degree phase. It's a static pattern, it has stopped rotating. And if I scan even further to the right, advancing the X signal, now it's rotating counterclockwise, and it rotates at the most rapid speed counterclockwise when I have it in counter-phase. And if I scan it all the way off to the right, now it is back in phase with the X and the Y, but in counterphase to the way it was before. Okay, how about instead of the first harmonic in X and Y against each other, we'll do the second harmonic in X and Y and see what difference that makes. So again, here we have a sandwich with a center surround in X and Y. And what happens if we advance the phase? Well, let's stop the oscillation here and take the phase of X here and advance it forward and see what happens. Click in the center of the square and drag to the right, and look what happens as we advance the X phase. So if we continue the simulation, we can see that as we change the phase of X, it changes from one kind of dynamic pattern to something completely different. Let's slow it down so we can see what's really going on over here. And I'm scanning to the right, and it goes past quadrature. So again, we have a static pattern that if we advance the X coordinate phase, then it begins to cycle. And if we advance it more, it cycles slower and slower, and now it oscillates in counter phase to the way it was. And now we go into negative quadrature. It rotates in the opposite direction, but because we're in the second harmonic, it doesn't do a single rotation about the center, but it does a double rotation across two axes. So again, this time, instead of the second harmonic in X, we'll go for the third harmonic in X and the third harmonic in Y. And what do we get? A static pattern that's kind of like a checkerboard. But if we advance the phase of X, you start to get rotations. Clockwise and counterclockwise symmetrical rotations until you get to about half phase, and then the pattern becomes static again. And then in the deeper advanced phase, the rotations go in the opposite direction until they reach quadrature. And then with phase all the way up to the end, they're back to a static pattern again. This is only the tip of the iceberg for a harmonic resonance system. In a sense, each of these nodes in the arrays at the bottom here are kind of like the cell body of a receptive field model. So the first harmonic in X will respond to this pattern in its input receptive field, or will project this pattern in its output field. But the difference with the harmonic resonance model is that when you combine different harmonics, you get combinatorial effective receptive fields. So it's not just an array of receptive fields to represent spatial patterns, it's and all the combinations of those spatial patterns as added and subtracted by constructive and destructive interference in a wave-based mechanism. Part 8, Harmonic Gestalt. Gestalt theory has always posed a profound challenge for neuroscience with its peculiar properties, emergence, reification, multistability, and invariance, in which the principle appears to be that the interaction between innumerable local forces simultaneously and in parallel produce a global gestalt, reifying the most regular interpretation and thereby suppressing its alternatives, or becoming multistable between them. Harmonic resonance exhibits exactly those properties. So, a harmonic gestalt theory to combine harmonic resonance with gestalt theory suggests that the visual system reifies every possible alternative in parallel as it picks the simplest alternative by the principle of Prägnanz, or gestalt goodness, gestalt simplicity. Detection and completion are one and the same process. It is the symmetry of the simplest perceptual interpretation that allows it to amplify itself by resonance. The very concept of this computational solution seems completely implausible in the absence of a harmonic resonance principle. So Gestalt involves a simplicity metric, or Prägnanz. So, for example, for this particular stimulus over here, perception seems to prefer this interpretation because it's simpler than the alternative. There's a hierarchy of Prägnanz. For example, an equilateral triangle is more regular than an isosceles triangle, which is more regular than an irregular triangle. And likewise with the square, that's more regular than a rhombus, more regular than a parallelogram, a trapezoid, or an irregular quadrilateral. So Prägnanz is a function of the information content of the shape. The shapes that have more articulations require more information to record their parameters. The tendency towards Prägnanz in perception is the perceptual equivalent of Occam's razor. The simplest interpretation is most likely to be right. So what appears to be happening in perception is a kind of inverse projection where the two-dimensional retinal input is projected in depth into a spatial representation, and from whence interactions between the different interpretations lead to the emergence of the most probable one, and at that point the other alternatives fade. In 1960, Hochberg and Brooks devised a quantitative metric for Prägnanz. They presented a bunch of ambiguous stimuli like these to subjects and asked them to rate which are more likely to be perceived as 3D shapes and which are more likely as 2D shapes. And then from these experimental results, they devised this quantitative metric that you count the number of sides of the same length in each of these figures, and the number of angles of the same size, and we compare this metric for 2D versus 3D interpretation, and it will explain these experimental results. So, for example, for this figure here, which tends to be seen as 3D, but it can be seen as 2D with the help of some colored lines, and if we count the number of sides, there are 16 different sides and 5 different sides lengths for this 2D interpretation. On the other hand, as a 3D figure, it has 12 sides and 1 side length, and all the angles are equal. So this metric accounts for the perception of Prägnanz. This is an interesting problem because it exemplifies the computational issues inherent in the problem. First of all, it requires human observers to see the 3D percept in the first place. Can we automate the process of spatial perception? This is a profound challenge that requires an unconventional approach. I propose a harmonic gestalt, sound from structure, based on the principle that a line will vibrate at a frequency which is the reciprocal of its length. Frequency equals 1 over length. So, for example, in this percept, this vertical line over here would be represented by a musical tone. That is a function of its length. If we now take a look at the two-dimensional percept and we employ a different tone for each line length, then you will get a sound like this. Here, on the other hand, is a three-dimensional percept, and this has a single tone. It is thus judged to be the most pregnant. So the frequency of a line is 1 over its length, and this representation is by its very nature invariant to rotation, and it's invariant to translation. All of these lines would make exactly the same tone. The invariance is a property of sound and other wave-based systems. This simple property has extraordinary consequences when using sound to represent structure or structure to represent sound.
This is my Harmonic Gestalt program written in Python using Matplotlib, available from my GitHub site. It presents a stimulus screen. If you click on the screen, it produces a stimulus point. If I put on another point, we get a musical tone, and the frequency of that tone is a function of the separation between the 2 points. Down here we see a Fourier transform. There's the DC term at the center. The left and right sides are symmetrically identical to each other. So this is just one frequency. These 3 peaks here represent one dominant frequency that varies as a function of separation between the dots. Now, if I add another point, let's say over here, the distance between these 2 dots and those 2 dots is about the same. But now we've got a new frequency over here.
Very faint.
Due to the proximity of these 2 points, we can see that over here on the Fourier transform as the peak out here. And if we move this point slowly to the left, this distance increases as this one reduces and this one stays the same. And what you see, let the audio catch up, is a change in the harmonic content of the sound as a function of the configuration of the 3 points. When the 3 points get close to an isosceles configuration, you can hear an extra harmony in the tone due to the fact that it's now reduced to a simple 2 peaks. And if we now move this dot up and listen to the change of tone, as these 2 sides get longer, then these 2 peaks approach each other. And as we get to an equilateral configuration, these 2 peaks merge into one. You have to find the sweet spot where it's in perfect harmony. There we go. So there's the perfect harmony of the equilateral triangle. This harmony is independent of the orientation of the pattern. It's a totally intrinsic metric. And to some degree, it is also invariant to the scale of the pattern, because although when we scale the pattern smaller, the frequency goes up, but what happened there? But the basic waveform, the fact that it's a single peak for this equilateral configuration, remains unchanged through the scaling.
So we have a representation here that is translation invariant, it's rotation invariant, and to some extent it is also scale invariant. That is because it employs an intrinsic metric, as does Clifford algebra, in which everything is relative to everything else. It's a relative scale. Now, we talked about the hierarchy of Prägnanz and how Prägnanz is a function of the information content of the shape. In terms of a harmonic theory, we can say that Prägnanz is a function of the energy required to sustain that resonance. So the tendency towards Prägnanz can be seen as a loss of higher harmonics due to impedance, and therefore it tends to favor a lower resolution, lower harmonic representation if it fits.
If we click points randomly on the screen, we get an ugly, inharmonious sound. Here's a harmonious tone from 4 points in a line. Equilateral triangles pattern. In fact, any pattern that has symmetry or periodicity is guaranteed to register with high Prägnanz. If we have two stimulus points on the screen with the corresponding sound, these 2 points themselves suggest other points that are in harmonious agreement with them. For instance, this one here, observe the peak out here becoming a single peak when it's most harmonious. Or maybe we can move this one over this way. There we go, that sounds better. So every dot that you add changes the field around it.
Part 9, Feedforward and Feedback Model. So far we discussed the feedforward model, where the presence of a pair of stimulus points creates a musical tone. That tone, in turn, creates a field around those 2 points, highlighting points that are consonant with them. So here we see a grid of points all at the same separation and thus frequency as the original pair of points. This whole grid is suggested by the presence of these 2 points. But there are other alternatives. For example, this equilateral triangle thing is also consistent with these 2 points. But these 2 patterns are kind of rivalrous because they can't coexist with each other. Here's the superimposed both patterns at the same time. But if we now add 1 dot here, that excludes the possibility of the square grid pattern and reinforces the equilateral triangle interpretation and changes the whole field around the model. Other sorts of feedback that would be expected from a feedback model is that when you have a linear resonance between 2 feature points, then this resonance will tend to expand outward at right angles to the original line by the same principle as Huygens' principle A line of point sources propagates as a wave at right angles to the line. So from a triangle, we would expect the linear resonances between the features, and then waves propagating at right angles to those lines inwards towards a center, and they reflect off each other at the center and propagate back out again. So the triangle resonates in and out between its perimeter and its center of symmetry. The same kind of feedback would be expected to propagate outward from the triangle, and this kind of propagation would account for the Gestalt grouping between features. And we see a propensity for this kind of symmetry and periodicity in art and ornament. Another kind of feedback we would expect from a linear resonance is seen in the harmonics of a vibrating string. In a full harmonic model, there would also be responses at higher harmonics. For instance, this interval here would be harmonious with its higher harmonic. Because this higher harmonic splits the interval into two equal intervals. This is not the only harmonious tone. There's also one to be found out over here, which is harmonious with the fundamental. It's the third, because they divide the interval into three equal units. And likewise, if we move this one to 1/4, this one to 1/2, and this one to 3/4, we get the fourth harmonic harmony. So in the feedback model, that would correspond to this linear resonance revealing its higher harmonics up to a certain level. And this is very reminiscent of these Chladni figure patterns. Mary Waller in 1961 recognized the resemblance of these patterns to ornamental patterns in human ornament. Here are some patterns of ornament from a number of different cultures and periods. Part 10, the Grassfire algorithm and Harmonic Gestalt. The Grassfire algorithm is an algorithm used in image processing to compute the medial axis skeletons of various geometric forms. And the way it works is you ignite a metaphorical grass fire around the perimeter of the object, and then you trace the flame fronts as they propagate parallel to the initial flame front, and record the points where they intersect or where they meet in the middle, and that is the medial axis skeleton of the geometrical form. Now, actually, this algorithm implicitly encodes Huygens' principle that the waves propagate at right angles to the line. This is significant. So I propose a symmetry completion computational process through the medial axis skeleton. This is the reverse Grassfire algorithm. Starting over here with A, we begin with a 3/4 circular perimeter, and we ignite a grass fire that propagates inward towards the center. All of the flame fronts meet at the center. If you record the arrival of waves from various different points in the circle near the perimeter, there will be the early arrival of the first flame front and then a late ending of the last flame front. And the closer you get to the center, the shorter but more intense the time trace. And at the very circular center, you get an impulse function that records the perfect symmetry at the center of even a three-quarter circle. I propose that this is followed by a reverse Grassfire rebound of the waves after they collide with each other at the center, and they propagate outward for the same time interval that it took for them to propagate into the center. And when they arrive at that point, they stop and print the flame front, thereby completing the symmetry of the circular symmetry detected in the stimulus. This part of the process, reducing a circular arc to a point, is the principle of abstraction. This, taking the circular symmetry of the point and propagating it back out to the whole circle, is a process of reification, completing the pattern based on the symmetries detected in it. So, with the Kniza triangle, we could expect it to work something like this. Over here in this corner, we see two edges that intersect. So this suggests an occlusion, but it could actually be an occlusion this way, or it could be an occlusion that way. How can we tell which way the occlusion is? Locally, there's not enough evidence to determine that answer. This is how I propose the system works. First, you get a perimeter response around the perimeter of the partial circle, which propagates inward towards its center of symmetry. And there, the incoming waves collide with each other and radiate back outward again. And now, at this point, there's a stark contrast between the symmetry prediction that says I should be seeing a circular arc right here, and the actual image where there's no arc there. And therefore, now it becomes reasonable to assume that this is the kind of occlusion we have. Now, if this same process was happening at the other two corners all at the same time, then the three completions will propagate into a center where they create the illusory triangle. The illusory triangle then radiates inward and finds its own center of symmetry, from which it bounces back outward. And where it strikes the circles, it completes there. So the whole figure resonates in and out as a unified gestalt. All right, now harmonic gestalt in 3D. Everything described so far in 2 dimensions extends naturally into 3D by the same essential principles. Imagine a 3-dimensional volume of point oscillators, each point oscillating and radiating waves outward and establishing connections to other points. This would now produce an emergent global oscillation of the whole shape. Symmetry and closure promote resonance. So we now have translation, rotation, and scale invariant representation in full 3D, using an intrinsic metric, using the ratio of the side lengths, and doing it now in full 3 dimensions in the nature of a Clifford algebra multivector. So now imagine that the front face of this cube is an input stimulus in 2 dimensions, and the volume of the cube is used to express the 3rd dimension. So each of these points in the volume has its corresponding shadow here on the input screen, but the way it works is that the input points are given first, and there they tend to create an oscillation somewhere along their z-dimensional, 3-dimensional line, and these points are free to slide in and out along these rails until they reach a more harmonious configuration. For example, if the input stimulus consisted of these 4 points and another 4 points, and each one of these creates an oscillation in the volume, then these points will tend to slide along their rails, because in this way they can create a more harmonious configuration.
Here's my Harmonic Gestalt 3D program. This one also presents a stimulus screen where you can click to produce a stimulus spot. This time it also presents a three-dimensional percept as an inverse projection into depth of this two-dimensional spot. So wherever this spot happens to be in two-dimensional space, this line here can be considered a probability density function of the probable location of this point in depth, given its location in 2D. Now in this simulation, we also have a slider here where we can adjust the value of that point in depth. Now we can add another point, and we get a musical tone. Here you can see a single frequency peak. And now we'll add an isosceles point in here, and we'll tune the location until it sounds harmonious. With two peaks in the Fourier spectrum. Now what we're going to do is we're going to adjust the depth of just this top point. And here we go. Moving inward in depth, you can see the slider change. And the dot moves. And if we give the sound a chance to catch up, it changes the tone. You see the two peaks of the Fourier approaching each other now. And now there's back to a single peak. What we have here, that's gone a little too far, come back a bit. And what we have here is an isosceles resonance, equilateral resonance in 3D to an isosceles stimulus in 2D, showing how this isosceles triangle can be viewed as an equilateral triangle in depth.
Okay, so we've discussed the forward problem. Given three oscillators in a equilateral configuration, we will produce a certain tone. Now the inverse problem is how do we find that triangle? Beginning with the stimulus provided from the input, how do we do this? What this is the inverse optics problem. For each edge of the triangle, we want to do an inverse reification of all of the possible lines at different angles and depths that could have projected to this line. So it's a field, a probability field in 3 dimensions, and on that probability field, we hope to discover some resonance. And here we have an isosceles resonance as in the stimulus, but you could also hope for an equilateral resonance for the same stimulus, and that this one being more harmonious will be preferentially perceived. Now this is an impossible computation unless implemented in a parallel analog wave-based mechanism. The fact that the visual system solves the inverse optics problem involuntarily, effortlessly, and instantaneously is direct evidence for a harmonic resonance representation in vision because no other computational principle is able to reify an infinite range of possibilities simultaneously and in parallel. A couple of quick examples. Here's a diamond-shaped stimulus that can also be perceived as a square tile in depth, tilted in depth. And here is the inverse projection of the diamond. And embedded in that inverse projection is a perfect square stimulus that fits into the extruded diamond. Here we see another example, this time the same kind of diamond, but 3 of them that pops into a cube in perception. Here is the inverse projection of the edges in the stimulus, and here we can see the perfect cube that is embedded in that inverse projection. How do we know that cube even exists? We can see it right here, although we have to use our perceptual system to see the cube. Likewise, with this example here, we have a stimulus that's an ellipse, but it can be perceived as a circle in perspective. Here's the inverse projection of that ellipse, and embedded in that inverse projection is at least one circle and also another circle tilted at a different depth. And therefore, this is a bistable percept where this can be seen either as a sewer cover in front of you or as a ceiling light above you. Those are the two alternative perceptions here. Of the infinite range of irregular ellipses embedded in the inverse projection, there exists one or more perfect circles tilted at just the right angle. Here we see another ellipse. This time it's wrapped around like a tin can stimulus. Again, we can do the inverse projection of these edges, and embedded in the inverse projection, there's a perfect cylindrical can embedded in that stimulus. So what is the evidence for this fantastically elaborate, highly speculative, and underspecified theory of vision? Well, here's the evidence right there. Do you not see it the way everybody else does? Perceptual modeling emphasizes that you can model the experience itself without regard to the underlying neurophysiology. You don't need to know the details of the neurophysiology to realize that the output of visual processing is a reified spatial image. Take a look at this example, a little bit too much to absorb in one glance, but observe how as you glance around the figure, different parts of it reify themselves until you get an impression of the whole. Is it valid to take the evidence of your own visual experience as evidence for the computational principles of perception? Because if it is, then it suggests that there's an explicit spatial field-like computational principle in the brain based on completion by symmetry. The principle of reification is perhaps the most underappreciated function of perception. A holistic global first principle of operation is highly suggestive of a wave-based resonance representation. Part 11. Cortical maps. Continuing in the vein of wild speculation, I propose that wherever you see oscillations in the brain, they are evidence of a standing wave oscillation in the brain, and that adjacent brain regions oscillate in synchrony with each other. And indeed, there is a global synchrony of the cortex with the subcortical regions, and of course, a synchrony across the whole cortex. There are likely also oscillations of the whole brain, synchronous oscillations, as well as perhaps oscillations left and right and top and bottom and whatever. I propose that the gyri and sulci of the cortex demarcate the standing wave patterns in different areas, with the sulci acting as nodes of oscillation, while the gyri serve as spatial maps of sensory or motor space. I propose that the oscillation pattern predated the emergence of gyri and sulci, being present when the embryonic cortex was smooth. I propose that it was the standing waves across the smooth cortex that first governed the formation of gyri and sulci. I propose that there are coherent resonance across complete cortical areas. For example, that the parietal lobe oscillates back and forth, and so does the frontal lobe in synchrony with the parietal lobe, and so do the visual and temporal cortices oscillate in synchrony as a whole. The cortical resonances are not just a simple back and forth oscillation. There are also components at higher frequencies that fill in the details of the larger patterns in a fractal self-similar manner. The spatial mapping of the primary somatosensory and motor cortices is not an accident, but is direct evidence for spatial processing in the cortex. For example, in the primary somatosensory cortex, the mapping of the face is presumed to be represented by patterns of activation in the neural tissue. The experience cannot be reduced to this flickering of cortical patterns of energy because there's also an explicit spatial experience associated with that cortical activation. But that spatial image cannot exist in some orthogonal space inaccessible to scientific scrutiny, but right here in the living cortex of the brain, where there is a neurophysiological mechanism to sustain that image. The symmetry across the central sulcus suggests a symmetrical wave-like oscillation between the sensory and motor cortices. And it is this wave that keeps the parts of the map in synchrony with each other. How do we paint images on the cortex using electrical activity? Well, let's take some inspiration from Jero Beam Fenderson, who paints images on his oscilloscope using sound. So noteworthy is that this is a cyclic representation. It paints the image again and again endlessly. It can either paint static images, the same image again and again, or dynamic images where the image shifts. The image is expressed in cyclic form so it can repeat. It uses an intrinsic metric, plotting the X against the Y, so this avoids the jaggies that you'd get from a raster scanning system. This is indeed the vector graphics principle. You paint out the whole image again and again. And the sound that you hear is not incidental. The sound is actually what is painting out the image. So in the next video, we've got a left audio controls the lateral deflection of the oscilloscope in X and Y, in X, and the right audio controls the vertical in Y.
We're gonna use our left audio channel for horizontal deflection and our right audio channel for vertical deflection. Now first we need a sine wave on our horizontal deflection channel and a cosine wave on our vertical deflection channel. Together they add up to a beautiful circle. We can alter its size and shape by increasing or decreasing the volume of both channels. Now we add a sawtooth waveform to the right channel. Our circle or ellipse turns into a spiral. To get this spiral into the shape of a mushroom, we need to multiply our left channel with a sine wave of the same frequency as the sawtooth. But we're only gonna use the sine's last quarter. Of course we want our mushroom to move, just like in real life. That's why we now add another sawtooth, multiplied with a cosine wave of a slightly different frequency, to our left channel. We can increase the number of mushrooms by dividing the cosine's frequency by 2, or even by 3. By randomly adding square waves, we get even more mushrooms. In fact, we can plant an entire field.
Part 12. Predictions for Neuroscience. Predictions for neuroscience. There are actual spatial standing waves in the brain that represent the structure of our experience. Binding through synchronous oscillations, it has been proposed that the synchronization of neural firing may serve as a means to group spatially segregated neurons that respond to parts of the same stimulus in order to bind these responses for further joint processing. Alternatively, the synchrony is a manifestation of a global standing wave that constructs the object in perception in which they are both sharing. The standing wave synchrony represents the whole figure, will be detectable between the feature detector neurons that are found to be synchronized. Predictions for neuroscience. The waves are not an epiphenomenon. The waves are the actual mechanism that performs the computation of perception. The competition between alternative spatial interpretations occurs not between high-level feature detector nodes, but by low-level voxel-by-voxel competition between waveforms in the reified representation. The brain is clearly capable of generating dynamic spatial patterns evolving in real time. The evidence of visual illusions clearly demonstrates the principle of reification in perception. The evidence of dreams and hallucinations clearly demonstrate the capacity of the brain to construct complete virtual worlds, complete with a self at the center of that world, as if that self were observing the world of experience. Neurophysiology. Where are the waves in the brain? Well, according to the neuron doctrine, the widely accepted default interpretation is that the neurons are quasi-independent computational elements that communicate by electrical signals propagated down axons and collaterals and transmitted to other neurons through chemical synapses. This paradigm is wrong. The fundamental flaw in this theory is the fact that extracellular recordings can record neural signals just as well as intracellular recordings, except that the polarity is reversed. The fact that extracellular recording is possible demonstrates that the cell wall does not insulate alternating voltage signals. The cell wall operates as a capacitor, and thereby the cell wall blocks DC current, but it does not block AC signals. So perhaps our notion of the neuron should be revised from the oscillations of single cells to the neuron as an antenna that radiates an oscillating signal outwards in all directions through the neural tissue. Part 13. Harmonic resonance in motor control. Let us examine the principles of motor control beginning at the lowest rung of the evolutionary ladder of animals with the lowly paramecium, a single-celled creature that propels itself through the water with wave-like motions of its cilia. Obviously, the synchronized motion is evidence of a wave-like synchronized process in the body of the animal without a single neuron or synapse or nervous system. And yet, this wave-like pattern has an element of intelligent control, because when the paramecium gets stuck in a dead end, it knows enough to reverse its synchronization pattern and to back out of the hole and to turn to a different direction and try something else. This is extraordinary intelligent behavior for a single-celled creature. Here's an actual paramecium swimming through the water. The principles of motor control can also be followed from single-celled to multi-celled organism, beginning with the Chlamydomonas, a single-celled organism equipped with two flagella that it waves in synchrony like a swimmer's breaststroke. This creature is also phototaxic. That means it steers towards the light, unless the light gets too intense, in which case it steers away from the light. The transitional creatures, Gonium, Pandorina, Eudorina, and Pleodorina, appear to be successive stages of more and more cells remaining stuck together as if by accident in a failure to separate during cell fission. The Volvox is the most sophisticated organism with a fixed number of cells. In all of these creatures, the flagella wave in synchrony, thus making the little multicellular creatures spin round and round in the water, and yet they are still phototaxic, steering towards the light. And yet there is no nervous system of any sort evident in these creatures. One level up, the Hydra has a nervous system. It's a multicelled creature with three layers, endoderm, ectoderm, and mesoderm. And the mesoderm is composed of a very primitive nervous system, much like a fishnet stocking, with primitive synapses that propagate waves in both directions. For example, if you stimulate a Hydra at one point, it generates waves of activation like the rings in a pond. And yet, this very simple creature is capable of some sophisticated behavior. For example, when it eats, it contracts its tentacle in the direction of its mouth while extending it in the opposite direction, and it extends its mouth to accept the food. The Hydra is also capable of a sophisticated somersault locomotion, whereby it contracts its body in the direction of desired motion and extends it in the opposite direction. Then, when upside down, it reverses the contraction and extension until its foot hits the ground, and then it reverses again to repeat the cycle. An extraordinary pattern of behavior for such a simple nervous system. Here are some animations of Hydra locomotion made by animated models based on observed behavior, for example, expansion and contraction. Looping, where it bends over, grabs the ground, skids its foot up closer, and stands up and repeat as necessary. Somersaulting, bends over, grabs the ground, flips its body over its tentacles, plants its foot back on the ground, and stands back up, repeat as necessary. And look at this, standing on its head and walking like a multi-limbed creature. This is extraordinary behavior for an extremely simple nervous system. Here's a centipede exhibiting periodic waves of motion of its legs. And here's another centipede. Six-legged insects have a number of characteristic gaits or sequence of moving their legs. And these patterns are sorted in sequence of how energetic the gait is. So the lowest energy ambling pattern that insects exhibit is a pattern where it's the right 3, right 2, right 1. These right legs are advanced in sequence, followed by left 3, left 2, left 1. Here's the left legs advancing in sequence, and so on. Repeat is necessary. Here's another time trace going horizontally, showing right 3, right 2, right 1, alternating with left 3, left 2, left 1, and so forth. If the insect is in a bit more of a hurry, it will start to overlap these. So we have left 1 and right 3, then right 2 and right 1 with left 3. So it's as if you took these and pushed them down to overlap by 1. And here is a double overlap gait that requires even more energy but produces more speed. And then there's the parallel wave gaits, where it goes back and forth between the two sides in yet another higher energy but higher speed gait. And here is the alternating tripods gait, a particularly elegant pattern whereby 3 of the legs, here shown in black, are planted on the ground and don't move, and the other 3, shown here in gray, are advanced forward, alternating with the reverse pattern where the ones that advanced before are now static and the ones that were static are now advanced. So here's the very elegant alternating tripod gait that many insects exhibit. And finally, there's the running gait, the highest energy gait, where you just run left and right as fast as you possibly can. Most six-legged insects can do 1, 2, or 3 of these different gaits, but always in the same sequence in a compromise between economy cruise and high energy run. The gaits of a horse exhibit the same kind of periodicity. Here's the ambling gait of a horse walking, starting with right 2, right 1, followed by left 2, left 1, much like the insect, right 2, right 1, left 2, left 1. Here we see the pattern shown in time. Here's the trot, where the front left and rear right alternate with the front right and rear left, a faster kind of motion than the walk. And here's the pace, where you alternate the right front and right rear with the left front and left rear, giving a swaying kind of motion. And here is the canter, where you have left front and right rear, alternating in a 3-phase with right front, followed by right rear. And finally, there's the gallop, the highest energy of the horse's gaits, where it's rear hoofs, front hoofs, rear hoofs, front hoofs. All of these are periodic patterns suggestive of an oscillatory principle of locomotion. Strogatz and Stewart, 1993, published an article, Coupled Oscillators and Biological Synchronization, whereby the variety of gaits available to 2-legged creatures exhibits the patterns of 2 coupled oscillators, and 3-legged creatures, like a man with a cane, with 3 coupled oscillators, and 4-legged creatures exhibit the harmonics of 4 coupled oscillators. Gallistel And von Holst, in 1980, performed a number of experiments on centipedes where they plucked off the legs of the centipede and observed how it changed their pattern of locomotion. So, for example, in this case, they plucked off all the legs of the centipede except for 4, or all the legs except for 4 with a spacing in between. And what they observed was that whether it was with a spacing in between or not, the remaining 4 legs of the centipede exhibited the gaits of a 4-legged creature. And this was true even when they amputated a number of intermediate legs, leaving only extremely remote pairs in synchrony with each other. When they amputated legs preserving 3 pairs of legs, then the insect exhibited the gaits of a 6-legged insect, regardless of whether the amputated legs were adjacent or separated by several limbs. That pretty much clinches the case. In the centipede, already generalizes to the pattern of 4-legged and 6-legged creatures. This is a multi-potential pattern formation principle where a simple mechanism can, with small variations, perform a multitude of different kinds of actions. Here is a bioluminescent jellyfish.
The bioluminescent jellyfish is a truly majestic creature. As they slowly navigate the ocean's currents, small cilia propel them forward into the depths of their watery surroundings. Because they can swim on their own, they are classified as nekton creatures.
Note how their cilia blink in different colors. This is caused by the chemicals luceraphane and luceraphis, which, when triggered, react together and cause a photoprotein to be created. This photoprotein is what gives off the glow, and different proteins create different colors.
You can find bioluminescent jellyfish in any ocean, but they're in the aphotic zone where they don't see the sunlight, and they are most commonly in the oceanic zone, away from the shore by the mid-ocean ridge.
And here is a bioluminescent squid. Observe the patterns on its skin. They are periodic cyclic patterns that are reified on every patch of its skin, and they reflect the patterns of muscular contraction of its locomotion. Here's a snake swimming through the water with periodic undulations under control. So when we observe the sinusoidal motion of a swimming snake or eel, we can see that there are patterns of contraction and extension on alternate sides of the body in a periodic pattern that is cycled through time, creating propulsive waves of undulation. But the eel has steerage control. It can still steer left or right by doing a greater extension on one side of its body and a greater contraction on the other. When this is added to the undulating propulsive activation, this creates propulsive plus steering combined signal, a kind of thing that is done very easily by harmonic resonance. The traditional notion of a motor neuron is the concept that each motor neuron branches to innervate a variable number of muscle fibers. So here is a motor neuron from the spinal cord that goes out into muscle and makes contact at various different points, and the motor unit includes each motor neuron and all the fibers the innervates. The innervation ratio can be up to 1 in 1,000, one neuromuscular junction for each 1,000 skeletal muscles controlled by it. This suggests a blurring of the motor control signal by a factor of 1 in 1,000, creating a less precise pattern of motor control. The alternative concept is a motor unit as a resonator that promotes a particular standing wave pattern in the muscle rather than dictating the exact contraction of each muscle. Part 14, Resonance in Visual Experience. In 1966, Heinrich Klüver performed an experiment where he gave subjects LSD, had them relax in a dark space, and record the experience that they had. The subjects reported seeing lattice, fretwork, filigree, honeycomb, chessboard, cobwebs, tunnel, and funnel patterns appearing spontaneously in their experience in a rapid succession, so they hardly had time to report their shape. It turns out that these kinds of hallucinations are seen in many other examples of neurophysiological stress, including falling asleep, waking up, insulin hypoglycemia, the delirium of fever, epilepsy, psychotic episodes, advanced syphilis, sensory deprivation, photostimulation, electrical stimulation, crystal gazing, migraine headaches, dizziness, and a variety of drug intoxications in our art and architecture. The primitives of visual perception. Artist Louis Wain in the 1800s made a profession out of drawing cute pictures of cats. He was then inflicted with a progressive psychosis that manifested itself in his art. His earlier pictures looked something like this, a perfectly reasonable picture of a cat, but observe the crazy immersion of chaotic periodic patterns above its head here in the background. His later pictures got more and more elaborate in color and in periodic patterns, and some of his latest pictures looked like this, where the image seems to completely collapse into total patterns of complete symmetry. When we observe psychedelic art, we see a common theme of the spontaneous emergence of symmetry and periodicity in ornamental type patterns. This one is Alex Gray, The Visionary Origin of Language. Here's another painting by Alex Gray, Newborn. I think it's a great depiction of what the experience of the newborn must be like. With overwhelming rainbows of symmetry and periodicity until he learns to view the world through all that chaotic confusion. And another Alex Gray painting, Over Soul. The central figure is like your unified consciousness, and the fragmented patterns is his mind expanding into infinity and at the same time shattering into a grid of eyeballs. The eyeballs are not a hallucination of eyeballs all staring at him. Those are all of them his eyeball, each one individually viewing the world. Here is an extraordinary animation by Stephen Hamann, artwork by Salvia Droid. Observe the relationship between the visual images and the sound. I propose that the sound that you hear in these extreme states of consciousness is the sound of your visual system painting out the patterns of experience. Part 15, conclusion. The evidence for a harmonic spatial representation in the brain is overwhelming. Harmonic resonance is the only plausible mechanism to account for the Gestalt properties of perception. Music, mathematics, and visual ornament are artifacts of a harmonic resonance representation. As long as neuroscience fails to detect pictures in the brain, it must be tuned to the wrong channel, because I know there are pictures in there, I can see them from the inside. It's time for philosophy to inform neuroscience instead of the other way around.